Hi friends, good morning. Myself Mr. Sanap, lecturer in Mechanical Engineering Department of Wagh Polytechnic, Nashik. Friends, today we are going to discuss about the normalizing and hardening. In case of normalizing, we are going to study the objective of normalizing, then procedure of normalizing, then temperature range of normalizing, and also we will discuss the advantages, disadvantages and application of normalizing. So similarly, we will again discuss about the hardening, then its objective, process and different defects are produced due to the hardening. So friends, normalizing or air quenching consists in heating steel to about 40 to 50 Celsius above its critical temperature and holding it at that temperature for a short time and then cooling in a air at room temperature. So normalizing is a frequency applied as a final heat treatment process to products which are subjected to high stresses. So we will discuss in next slide about the objective of normalizing. So the first objective is to produce the uniform structure of the metal, then to refine the grain structure of steels, may achieve required strength and ductility in a steel that is too soft and ductile for machining, then reduces the internal stresses to improve the structure in welds, produces stronger and harder steel than full annealing, and then eliminates the carbide network at the grain boundaries of hyper-eutectile steels, and in general improves engineering properties of steels. Then there is a procedure of normalizing. Then we will see the procedure. The first step, that is, it differs from full annealing in that the rate of cooling is more rapid and there is no extended soaking period. The type of structure obtained by normalizing will depend on the thickness of the cross section, as this will affect the rate of cooling. Normalizing produces microstructure consisting ferrite, that is white network, and perlite, means the dark areas, for hypoeutectile, that is up to about 0.8% carbon in steels. For eutectile steels, the microstructure is only perlite and cementite for hypereutectile steels. So the temperature range of the process depends on the carbon content in the steel, and these are given below. The first one, for hypoeutectile steels, 40 degrees Celsius to 50 degrees Celsius above AC3, that is upper critical temperature, and for hypereutectile steel it may be 40 degrees Celsius to 50 degrees Celsius above ACM, that is upper critical temperature. So we will see the advantages and limitations of normalizing. First, there are some advantages. It takes less time, then it is more convenient and economical. It gives slightly more hardness and toughness. Perlite is fine and appears unresolved with optical microscope. It raises the yield point, then ultimate tensile strength and impact strength values of steels. So we will see the limitations. The first one, it requires higher heating range than annealing. It produces steel with less mechanical properties as compared to annealing. Then internal stresses are more. Grain size distribution is less uniform. This cannot be used for complex shapes because air cooling may cause cracking to the material. Then there are some applications of normalizing. By completing the normalization of steel, the strength of the piece of steel can be improved compared to steel that is not normalized or treated with another heating process. The ductile performance of steel can also be improved through normalization. This is possible without reducing the hardness or strength, as can happen with other heat treatments. By using the normalization process, modifications can be made to the grain structure of the steel to make it usable for specific purpose. Then steels with low levels of carbon do not have their rate of ductility altered by using the normalization process. So normalization is used for steel parts that require the maximum amount of strength and impact strength. Then the next topic, that is the hardening. So hardening is that heat treatment of steel which increases its hardness by quenching and tempering. So the process of heating the steel above critical temperature, then holding it at this temperature for considerable time and cooling suddenly is called as hardening. So this sudden cooling is called as quenching. Tool and machine parts required to undergo heavy duty service are oftenly hardened. Quench hardening and tempering are confined in application to the so-called heat treatable steels, nodular graphite iron, and alloy cast iron. However, in steels, the maximum percentage increase of hardness by quenching is obtained if they contain between 0.35 and 0.60% carbon. Then there are some objectives and temperature range of the hardening. First we see the objectives: to harden steel to resist the wear, then to enable steel to cut other materials, to improve strength, toughness and ductility, to develop best combination of strength and notch ductility. Then there are some temperature ranges for hardening. The hypoeutectile steels, the temperature range is between 30 degree to 40 degrees Celsius above AC3 means upper critical temperature, and for hypereutectile steel the temperature is between 40 degree to 50 degrees Celsius above AC1, that is lower critical temperature. Then there is a conventional hardening process. Then we will see the step of the process. In this process, contain steel with sufficient carbon, that is 0.35% to 0.70%. So hardening is the process in which steel is heated up to 30 degrees Celsius to 50 degrees Celsius, that is above A3 line, then held at the temperature from 50 to 30 minutes per spec 25 mm cross section, cooled rapidly or quench in a suitable medium. Example may be quench in a brine, water or oil. Then produce desired rate of cooling and a suitably hardened steel. The degree of hardness of a produce in steel depends upon the following points. That is the first one, composition of steel. Suppose 0.35 to 0.50% of carbon steel harden more. Then natural and properties of quenching media, then quenching temperature, size of the objective to be quenched, homogeneity of austenite, degree of agitation, rate of cooling, surface condition of metal, that means it contains some impurities like scale on the workpiece surface, decreasing the hardening effect. Then there are some hardening defects: uneven hardness due to uneven and prolonged heating, then insufficient hardness due to long hardening temperature or too fast uneven heating, change in dimension due to heating and cooling, then fracture during cooling due to uneven heating or too fast cooling, oxidation and decarburization takes place due to high temperature, distortion and warpage may be created, mechanical properties not conforming to specification, and soft spots may be produced. So these are the hardening defects. Thank you.